Quantitative structure activity relationships, in short called as QSAR, mainly propagated by Sir Corwin Hansch somewhere from 1960 onwards. And there was one period where QSAR was a very popular approach. Basic aim of QSAR, though QSAR is a very broad term, and Hansch's LFER model is one of the methodology of QSAR, but when we commonly call QSAR, it comes to our mind the Hansch model. Like for example, photocopy is a real word, but we call it as Xerox because it's a very leading brand, something like that. The basic aim of QSAR is to develop mathematical correlationship between drug characteristics and drug activity. You can define it as a method to establish quantitative relationship between physicochemical properties and biological activities of the compounds, or in SAR where we are correlating the chemical structure of the compound with the biological activity. Here we are going one step further. We first transform the structure into a set of numerical descriptors of the drug's physicochemical properties, and biological activity is also converted into the set of numbers or in some numerical form, and now these are mathematically correlated. So you can express everything in numbers, means how much of this property in number can increase the biological activity or decrease the biological activity, how much, so how much will be the influence. Applications mainly are three. In a given series, you can optimize the lead to get a maximum activity compound. You can predict the structurally related analogs without synthesizing them from a robust mathematical model developed. And sometimes you can throw light on the information on the mechanism of action or what are the binding forces or prediction of the mode of action, etc. Advantages are very many. In case of QSAR, you can save a lot of time, efforts, chemicals, and even other costs on the synthesis of non-productive compounds. You can also avoid unnecessary biological evaluations, whether it can be any model. If it is an animal model, you can save the animals. There are various approaches. By far the most popular is the Hansch analysis. There is free Wilson, which we had already discussed. There are others like discriminant analysis, principal component analysis, factor analysis, cluster analysis, pattern recognition, and the mixed approach of Hansch and Free and Wilson by Hugo Cubini. Uh, Basically propagated by Corwin Hansch that biological activity is a function of physicochemical properties of molecules. Sir Corwin Hansch from the University of Pomona, USA, explained that biological activity of any drug is a result of two integral steps or events occurring in the body following the administration of the drug. First is after administration it gets absorbed and reaches the site of action, and second it's real action at the site of action. So Hansch, let us explain these two steps processes of Hansch in a more detailed way. After introduction of the site of action, or after introduction of the drug in the body, the drug travels to the site of action through various body fluids and passing through various body membranes, and for this purpose the drug needs optimal lipophilic or hydrophilic properties. Second is after reaching the site of action, which is the so-called receptor, it has to have a complementary orientation with the receptor to have a proper fit, and so the steric property. And not only that, Finally, the non-covalent bonding with the receptor, the drug should have appropriate electronic features, so the electronic property. And therefore, biological activity is a function of lipophilic, hydrophilic, electronic, and steric properties. So let us discuss these two steps one by one. So as we said, the drug after administration has to enter the bloodstream and reach the site of action, and this is by the virtue of its optimal lipophilic or hydrophilic properties. Therefore, the biological activity is a function of the appropriate expression of this lipophilic or hydrophilic property, which can be expressed by log P or pi, which is the Hansch lipophilicity constant. Or in other ways, the other step, after reaching the site of action, it has to orient properly by virtue of its steric properties, and it has to bind properly and interact with the receptor by the virtue of its electronic properties. So to this above relationship of biological activity plus A log P plus A1 log P square, we can add two more terms, and these are sigma, that is Hammett constant, and steric constant, stop steric constant. So the equation becomes biological activity is a function of A log P, that is the partition coefficient, or you can take the Hansch's lipophilicity parameter, you can take a single term, you can take a square term, and the Hammett constant and the steric constant. So it is correlated in this way. And since all these terms are, if you go into details, these are all log terms. Therefore, biological activities also should be considered in log terms only. So it is a practice to use the biological activity in log terms for the purpose of correlation in the QSAR. Also, as this all terms on the RHS, that is, these terms are related to the Van 't Hoff equation of linear free energy, biological activity is also related to these terms. So this is called as a linear free energy model. So it is designated as Hansch's LFER model. Now if you plot the graph of 1 upon concentration, that is the expression of biological activity, versus log P, that is the expression of the lipophilicity, it can be seen that for a limited range of log P values, say up to 1 to 4, you will get a direct proportionality and a straight line graph will be observed, showing a perfectly linear relationship between the hydrophobicity and biological activity. Okay. So you can express it in a very simple: y is equal to mxc plus mx plus c, that is intercept, slope, and this is the variable, and this is y. Okay, straight line equation. However, it does not happen like that. If we increase the number of compounds more, you are bound to land up with the increment in the log P to such an extent that at one particular point you will reach an optimum active value, which is called as the cutoff point, and that is a maximum or optimum log P. And then after beyond that point, any increase in log P will result in a decrease in the biological activity. So there will be fall. So you end up at this optimal you will end up with fall. So the equation becomes, you need to add a parabolic term or a square term. So instead of using rather a straight line equation, it is pertinent that we use a parabolic equation or relationship. So this is a nice explanation why Hansch's complete equation includes one square term. So incorporating all the three parameters and the square term, we are dealing with four independent variables correlated to the dependent variable, that is biological activity, and somewhere the Hansch's equation takes this form, and where C is the concentration of the drug and kappa is the lipophilicity Hansch constant, and sigma is the Hammett's electronic parameter, and ES is a Stark steric constant, and all these K1, K2, K3, K4 are the slopes, or these are constants, and the intercept is also constant. These are the various Hansch's molecular descriptors for these three parameters. Some are experimental, some are theoretical, and where their values are already there in the literature. Partition coefficient, mostly you have to deduce in the laboratory. Pi constant is calculated from the partition coefficients. Then you can deduce experimentally the reverse phase TLC RM values. You can find out the RT, that is the log K dash elution time by HPLC. For electronic parameters, you have ionization constants, you have various types of Hammett constants, you have got spectroscopic shifts, and you have resonance effect, you have field effect, you have ionization potential. For electronic parameters, theoretical, you have net atomic charge density, super delocalizability, energy of molecular orbitals, highest occupied molecular orbitals energy, and lowest occupied molecular orbitals energy. For steric parameters, you have the staff substituent constant. You will see it in details. We have van der Waals red ion volumes, molecular connectivity indices. This can be calculated. Molar refractivity experimentally can be determined. Para-Kerr can be determined experimentally. Interatomic distances can be found through computer models, and minimal steric difference can be calculated. So we are going to discuss three important parameters, or many parameters of the physicochemical properties, that is some of the lipophilic, some of the steric, and some of the electronic. But before that, it is pertinent that we should also see how the biological activity is expressed. So first and foremost is we should see how the biological activity expression is there in QSAR. It can be qualitative, it can be quantitative, but qualitative is out of question because we are dealing with quantitative structure activity relationship. So this part is of no use. You have to express the biological activity in some numbers. So either you express it as RFD, response for a fixed dose, like MST, percentage reduction, quantitative effects, etc., or dose required for a fixed response like ED50, LD50, MIC, IC50, like that. And second is more preferred because it is relatively not less prone to errors. And as you know, biological activity is always expressed in form of log P. Coming to the lipophilic parameter, we have the partition coefficient. These are equilibrium constants and are logarithmically related to the linear free energy of the model. So log P values are taken. So partition coefficient, we know very simply, if we partition a drug molecule between two phases, aqueous and oil phase, then the concentration in oil phase divided by its concentration in the aqueous phase is the partition coefficient. From these log values of partition coefficients, one can calculate Hansch's lipophilic substituent constants, and we'll see that also in detail. And invariably in laboratory, when we determine the partition coefficients, particularly of drug substances for QSAR studies, we use N-octanol as a lipid phase for various reasons. Here they are listed. It has a lot of structural analogy with the biological membranes and not affected by many of the solutes or the substances dissolved in it. It has one OH, so it has little bit of desirable polarity, and better than purely hydrocarbons like toluene, xylene, benzene, etc. It has low water miscibility. It is chemical stable, so it is separable. It's chemically stable and it's got low volatility, so accuracy is not suffered. It is commercially easily available and low cost. It has little bit hydrogen bonding and donor and acceptor property due to this OH. and a large database of results available using octanol water system is there in the literature. So what is pi? Let us see. So pi is basically given by a formula log partition coefficient of the substituted compound upon partition coefficient of the unsubstituted compound. X is substituted compound, and it therefore follows that if you try to solve this equation, pi is log px minus log ph. So in simple words, you can say the change in log p brought about by the substitution of h by substituent x is expressed by pi. So in other words, the log P of the substituted compound is nothing but the original compound plus the change brought into that, which is the Hansch lipophilic parameter. And a very simple additivity principle can be used. These lot of values are available through the determinations. If you know the log P of the unsubstituted compound, simply adding this will explain you or give the value of the appropriately substituted compound. Let us see one example of this. We are discussing here metachlorotoluene, and by experimentally they have found out its log P is 3.28, but you can also calculate provided you have the log P of either toluene or even benzene. What you need to know is the pi values of these substituents. For example, you have the log P of toluene, and if you have the pi value of 3-chloro, you simply add these two and you will get the log P of the entire metachlorotoluene. That is what, say, just toluene you have 2.69 and this is 0.71, so 3.4. Okay. Positive value of pi means it is a lipophilic substituent, and negative is electron withdrawing substituent. Like nitro will have a negative pi value. Or otherwise, still you want to simplify, you just take the benzene log P, and if you have available values of 3-chloro, you are already having 0.71, and for if you get for methyl 0.56, again it comes same. Pi values are of course affected by conjugation, so for you have different values for non-conjugated and conjugated systems. There are some anomalies or some exceptions in the pi value. Some cases pose some problems in their calculations, and non-additivity is also suffered. One such thing is the hydrogen bonding. Example, salicylic acid versus benzoic acid. Log P of salicylic acid comes out very less as compared to the calculated one because of the intramolecular hydrogen bonding. Okay, but if the same is done with para hydroxybenzoic acid, it comes higher. Steric effects, steric bulk or crowding also prevents access of water to the groups and log P increases. Uh, Say for example, orthomethoxy phenylacetic acid has higher log P than its para and meta isomers. But if the steric group themselves are polar, like in 1,2,3 trimethoxy benzene, then the log P drops. Practically, log P is measured by shake flask method, equilibrating solute between the octanol and water, and solute should be pure. Sometimes water, if it is plainly used, it should be doubly or triply distilled. Otherwise, in case of say acidic solutes, you take 0.1 normal HCl, or in case of basic, of course, you take 0.1 normal NaOH. And the determination after the shaking and separation is done by either UV or fluorimetry or HPLC or titrimetry. But the condition is the compound should be very pure, and the solvents buffer used should also be pure. It is bit time consuming, and reproducibility on a large scale when many compounds are to be determined is becoming difficult. And also the inherent solute are, if suppose highly water soluble, highly polar or volatile in nature, then it poses problem with accuracy. Second parameter is the electronic parameter, the Hammett constant, and that is the electron donating or withdrawing power of the group. There you have various parameters like pK values, you have various type of Hammett constants, you have got the resonance and field effects, you have the energies of HOMO and LUMO orbitals and atomic electron charge densities. But we are particularly focused on the sigma or Hammett constants, particularly for the aromatic cysteines. And what is sigma? It is, for example, the ratio of the dissociation constant of the substituted versus the non-substituted benzoic acid or that type of compounds, and it is correlated with this division with sigma with a rate sensitivity effect expressing constant rho. For benzoic acid, the value of rho is just 1. There are special sigma values for electron withdrawing and donating substance, sigma minus sigma plus. For also for resonance and inductive effects. For resonance and field effects, there are also Swain-Lupton constants. pK can also be additivity principle calculated if you know the sigma values. Only difference is pi was added. Here sigma is to be what you can say subtracted. How? Let us see the expression of sigma. Sigma is the ratio of log of dissociation constant of substituted upon unsubstituted. When you simplify this equation, log kx minus log k0 is rho sigma. Let us assume we are discussing about benzoic acid series, so this becomes 1. So sigma is log substituted benzoic acid minus log benzoic acid. If the negative log is a positive pKa, so this becomes pk0 and this becomes minus pkx. So if you want to see what is pkx exactly, that is the dissociation constant of substituted benzoic acid, you bring it to the RHS and you transfer this sigma to the LHS. So it becomes pkx is equal to pk unsubstituted minus sigma. And let us work out an example for that. If you want to calculate the pK value for paranitrobenzoic acid, you only need to know the pK value of the benzoic acid and the sigma of the para 4-nitro. So you just deduct it from this and you will get the value. And it is but natural that paranitrobenzoic acid will have a lower pKa than benzoic acid because paranitrobenzoic acid is a stronger acid. Third is the steric parameter, where we have the top steric constant. This is also something like log K upon K0, but this is for the acid hydrolysis of aliphatic esters. That was for benzoic acid dissociation constant. This condition is under acidic condition. Okay. There are other geometrical descriptors like van der Waals volume and van der Waals radii, then minimal steric difference, and these are the stereomolar Verloop's parameters. And we have some typical calculatable descriptors or topological descriptors, which this deals with the arrangement of the molecule, which are called as molecular connectivity indices of 0 order, first order. You can even go further. They are expressed by a symbol chi. So 0 order is chi raised to 0 is a sigma of 1 upon the square roots of the carbon numbers. So basically I have taken here an example of simple N-butane, and I number the carbons as per their nature. Whether they are primary, I have numbered them 1. If they are secondary, I have numbered them 2. And you just do the 1 upon their square root sum total. The sigma of this, they are 1 upon the square root. So that is a zero order molecular connectivity. In first order, what you do is you assign new numbers to the bonds which are the products of the two joining atoms. So 2 ones are 2, 2 twos are 4, 2 ones are 2, and now you take the 1 upon their square roots, you will get the zero order molecular connectivity. Let us go through the methodology of QSAR. You need to understand little bit of statistics, and basically we need to synthesize compounds, we need to screen them, so we have the biological data, we need to express it properly, then we need to deduce there 3 types of physicochemical properties, and then with a computer program which requires statistical validation, we have to correlate the results. That is the simple methodology, but before that we have to understand what is the principles of regression analysis, because the methodology used is called as a simple multiple or multiple linear regression analysis. Few definitions. First is the sum total of all the results. Like I have taken here an example of 7 students and their heights. The sum total of the heights will be called as a population. So observations, whatever observations, their sum total sigma is called as a population, and the sample is called as n. So here n is 7. So population divided by sample is arithmetic mean. So average height is 152.1. Now sum of squares of deviation. So from this, each is how much deviated is done by SS mean. Like from this, each of this value is subtracted, and then the resultant value is squared and summed up like this. This is the average value. These are different values, and they are squared, and you got this. And this, if divided by n minus 1 square, that is the number of observations minus 1 square, what you get is the standard deviation. The sixth term coming in this is standard error of mean. The standard deviation divided by square root of the observations, number of observations, is called as standard error. And the seventh part is the probability estimation and hypothesis testing is given by student t value, which is basically depending on the degree of freedom. So the student t value corresponding to the degree of freedom is found out from the statistical tables, and degree of freedom is nothing but number of observations minus 1 minus number of independent variables. So suppose if I am working with 15 compounds, and if I have 3 parameters, steric, electronic, and lipophilic, so 15 minus 1, 14, 14 minus 3 comes to be 11. So my degree of freedom will be 11. In the statistical table for 0.05% probability level, I should check against 11 degree of freedom what is the t value, and that my t value should come lesser than this t value, and my t value will come after I perform the regression analysis of correlation through computer. In other words, the t value is the value of the coefficients divided by the errors of the standard error of the coefficient. Coefficients are the slopes for each parameter. So now we actually go for working, and we prepare a data table, and all parameters are put, dependent and independent. Dependent is the biological activity. We draw the structure, we enter the substituents, biological activity, log values are found, parameter values are put, lipophilic, square of lipophilic, electronic, steric, indicator variable, whatever. How many regression equations we can perform is given by the formula 2 raised to independent variables minus 1. So if you have got 3, then 8 minus 1, that is 7 equations. How 7 equations will be there? First, second, third, 1 parameter is correlated with biological activity, and 4, 5, 6, 2, 2 are correlated, and in 7 all are correlated. And before you proceed for further step, you have to first establish that these independent variables are not intercorrelated, otherwise it will cause error. Okay, now once you perform the regression analysis, like putting the value compound wise, the log biological activity value, then the program will ask you enter the value of the steric, enter the value of electronic, enter the value of lipophilic, enter the value of lipophilic square, and it will go on asking you. Before that, it will ask you how many compounds are there. So that many times it will ask you. So you need to have that table ready. Once you do that, then it will ask you perform regression analysis, and you give enter. It will give you the results, and you will have to then write the equations interpreting the results. So basically, you have to see, you have to apply certain tests to see that the results are statistically valid and not just chance correlationships. So I found 5 equations. One is a complete equation with all parameters pi, pi square, sigma, and chi, that is a steric. I did it with say 18 compounds. My standard error came very less, fine. My regression coefficient, which actually shows that there is a correlation between the biological activity and the independent variable. If it is very good, it should be somewhere between 0.9 to 1, but not 1. That is very good. And generally for QSAR, something about 0.9 plus is acceptable. Second is the coefficients of the variables, which I have expressed in green color. As far as possible, they should be in full numbers and not in decimals. So this shows this property has a strong influence on the biological activity compared to this property. While here these 4 and 5 equations, in all respects they are failing. Either their regression coefficients are very low, there only they are rejected, and these coefficients are also very low. Some places this coefficient is lower than its error, and so the student t value will be very poor, very poor. It will be more than what is expected. And from degree of freedom, now like for 18, and you have here 4, so 18 minus 1, 17 minus 4, your degree of freedom is 13. You should get a value less than 2.16. This is a table value. Your value should be less than that. There is also something called